So today we're very happy to have Valentina Bisogni to actually speak about a direct observation of a Magnon spin current by resonant inelastic X-ray scattering. This is actually extremely important experiment in the sense that this is actually the first time the Magnon motion has been seen by any technique, as far as I know. I mean, any spectroscopy technique, I should say, more precisely. Yeah, so I'm very excited to hear her talk. Yeah, please get going. Yeah, it's all yours.
Yeah, thanks a lot again for this kind invitation. I'm very happy to contribute to this colloquium series, which is indeed very nice and convenient on YouTube. Thanks for the link. So as Pencheng just said, I'm going to talk about our recent work that appeared 2 months ago in Nature. And it is about observation of spin current by resonant inelastic X-ray scattering in Yttrium Iron Garnet. So this is the outline of my talk. I will break it into 3 parts: a general introduction to Magnon transport and Magnon current. I will then present a new approach to probe the Magnon current that is based on resonant inelastic X-ray scattering, in short RIXS. And I will then present and discuss our results about observation of Magnon current in Yttrium Iron Garnet. So let me start by providing a little bit of context here. So in the last decades, the growing demand for faster, smaller, and energy-efficient electronics really stimulated the search for what I call exotic forms of transport, which are basically not based on moving charges. And in this context, Magnon transport is representing a very concrete alternative to conventional electronics, and it is based on the flow of the spin angular momentum. More broadly, Magnon transport can use all different types of collective spin excitations. I mean, if we are using then magnons, we can then have a Magnon current, we can use spinons for spinon current, and going on with this logic can also exploit superconducting spin singlet or triplet, and also fermion-based current. So what is the main key point behind then this type of transport? So without having moving charges, essentially we benefit of reduced heat dissipation. So if we think about conventional transport where electron conveys the form of energy here, they go around the material, but at the same time, they also scatter into each other, into other quasi-particles like phonons, causing actually a dissipation of energy by, for example, Joule heating. But if now we get rid of the moving charges and we base our transport simply on the flow of the spin angular momentum, as represented here by this Magnon wave, we are now gaining a lot in terms of reduced heat dissipation. Therefore, we have an option for very energy efficient type of transport. And going on in this direction, we can basically extend Magnon transport to be performed in insulators. So now we get really rid of any form of electron-electron scattering, having virtually zero losses by Joule heating. We can benefit of faster performances and also of longer propagation distances for the magnons in insulators. So all of these are very promising advantages of Magnon transport. Okay, sorry, I had some difficulty switching. So now, in order to gain control of this new type of transport, we need to basically understand how to generate a Magnon current and how to measure a Magnon current. So regarding the generation of Magnon current, there are several approaches, and I'm listing here a couple that are, in my opinion, the most common or most used ones. So the first one is the one on the left that is based on spin Hall effect and spin orbit torque. So basically we have our conductor that is now a magnetic material as represented here by this gray slab. And on top, we have an electrode that should be non-magnetic, like, for example, from platinum. So first, we realize the spin Hall effect in our platinum electrode by having an electric current going through it. And this electric current transfers to the platinum electrode, generate a spin current across its thickness. Because of the spin current by spin Hall effect, we now have a spin accumulation at the interface with the underneath magnetic material. So the spin accumulation can actually generate now an oscillation in the magnetization of our magnetic conductor by spin orbit torque. And because of this, magnons get excited in the material and they can finally generate a magnon current. Another approach, which I represented to the right, is by Spin Seebeck effect. So here, similarly to the regular Seebeck effect, we are dealing with a temperature difference or temperature gradient across our now conductor, that is again a magnetic medium. And because of this temperature gradient, we now generate an imbalance in the spin electrochemical potential. And because of that, we are driving now a current across the material in the direction anti-parallel to the temperature gradient. As it regards instead the measurement of magnon current, the most common approach that we can find is based on inverse spin Hall effect. So we can refer to the picture here on the right, where we have our magnetic conductor with a spin current inside. And now to detect the spin current, the most used approach is actually to create an interface with, again, a metallic material that is non-magnetic, and usually can be platinum again. And now the spin current gets injected into the platinum, and by inverse spin Hall effect, it is now converted into an electrical signal, like this voltage here. By measuring the voltage as a function of, for example, temperature gradient, as I represented here in case of a Spin Seebeck generated current, we can see that the voltage measured across the platinum increases as we increase the temperature gradient, which means that actually we are increasing the amount of spin current created in our material, and it is found a very linear proportionality between the spin current and the measured voltage by inverse spin Hall effect. So while this is a pretty effective method to measure and to deduce the existence of the magnon spin current, I need to warn that this is an indirect measurement. And it is actually the most convenient approach, because as an alternative, it is just simply too hard to measure the direct signal that comes from the weak electric field associated with the flow of spin angular momentum. So it's simply not possible to macroscopically measure a magnon spin current directly. But also, we need to be aware that this indirect process actually relies on several interfaces related processes and conversion phenomena as well, which basically hinders the microscopic understanding of the magnon transport process itself. So here it comes then the question, how can we observe the magnon that contribute to the transport phenomena in our material with an energy and momentum resolution to better understand the flow of energy? So to answer this question here, I'm proposing what I call a new approach. So let's start by considering how we normally measure spin waves, magnons, in material, and now actually we can effectively measure magnons then in a device. So normally when we want to measure magnons, we can deal with a long list of techniques that give access to this information. And here I'm just listing the major ones like Raman scattering, brilliant light scattering, electron spin resonance, inelastic neutron scattering, spin polarized eels, and resonant inelastic X-ray scattering. So next, if we are interested in the energy versus momentum dispersion, we basically get rid of the first three techniques as they are limited to momentum zero or very close to zero. So now for energy dispersed information about magnons in material, we are left with a second group here of technique. But now, as in this talk, we are interested in devices that normally involve small amount of material, and most of the time we need to deal with the presence of electrodes. We basically rule out inelastic neutron scattering because of the volume involved, and spin polarized EELs because it's a very surface sensitive technique. So this leaves us with an open option that is resonant inelastic X-ray scattering. So let me briefly introduce this technique then. So resonant inelastic X-ray scattering is a photon in, photon out process. To perform this technique, we need very specific conditions based on a synchrotron accelerator and on a beamline to produce monochromatic X-rays. So we shoot our monochromatic X-rays to our sample, and those need to be tuned in energy to resonate with a very specific transition in our material. For example, to promote a core electron into an open energy level in the conduction band. This step actually on its own corresponds to the X-ray absorption of the material under study, for example, as it's shown here for a copper-based oxide. Once the system relaxes back, it can do in various ways. Among them, we can now consider an electron from the valence band that goes back to fill the empty core state. And after this process, we have then an emission of an X-rays. By analyzing in energy the emitted X-rays, and since we know, because we tune the incoming energy, we are basically finding out the energy loss that we have transferred to our material, to our system. And this energy loss corresponds actually to the energy needed to create an excitation in our system. And this is what is the information that we record in our RIXS spectrum. In reality, the RIXS spectra are pretty dense. There is a large number of peaks and excitation we can be sensitive to. And we can find, for example, excitation corresponding to phonons, plasmon, magnons, and at higher energy, usually in the EV energy scale, we can have orbital DD excitations and at even higher energy charge-related excitations. And all of these modes are actually captured in a RIXS spectrum because indeed, this technique, it is sensitive to all the electronic degrees of freedom as I represented here. And as a general overview, if we talk about resonant inelastic X-ray scattering in the soft X-ray energy range, so between 200 and 2000 eV, we can actually study a large variety of excitations. Of course, since this is the main topic of this talk, we can probe magnetic excitations, and there are momentum dispersions in a large variety of material, always provided we can satisfy the resonant conditions. We can understand the ground state electronic configurations of material. It is possible to measure phonons, and through the multi-phonons branches, one can extract electron-phonon coupling. We can look at very weak ordering phenomena, as it was indeed found like a CDW ordering in cuprates by performing energy-resolved resonant elastic X-ray scattering and getting rid of all the other excitation that normally contaminate the elastic signal. We can access plasmon, so charge volume excitations and their dispersion. Another important sector is access to orbital crystal field excitations and also excitons. And even more recently, it has been found that RIXS, it is sensitive to excitations connected with single photon emitters. Now onto the instrumentation that is required to realize this technique. I would say it is pretty spectacular and interesting. So in order to perform RIXS with very high energy resolution, one needs to have extremely long beam lines, around 100 meters, and extremely long spectrometer arm to analyze in energy the scattered X-rays from the sample. And what I'm showing here is the SIX beam length that we have here at NSLS2 of Brookhaven National Lab, where we have this 15-meter spectrometer arm moving in the horizontal scattering plane. And this instrument, it is capable of an extremely high resolving power, reaching around 35 to 40,000. And since it can move, as this video is showing here, from 40 to 150 degree of scattering angle, we can explore a pretty large variety of momentum transfer. Now let me do then another step forward in this direction and discuss how actually the specific beamline here, it is ideal to answer the question that here we are interested in. So for example, studying Magnon current in a device. So first of all, because there is a very high energy resolution that it is needed to measure low energy spin excitation as well as their energy shift as a function of momentum. And in here, I'm just showing some recent example measure in other iron oxide compounds. We have high throughput that is effective on very small sample volumes or very ultra thin samples. Like here, we did a study on iron thin films down to 3 unit cells, so 1 nanometer of thickness. We are dealing with a very small X-ray beam that is 1 micrometer large in the vertical direction. And this is ideal to study very small samples, but especially devices, as I'm representing here just an XY scans of a recent sample that we measured. And finally, we have in situ electrical setup called Opera to really realize operando measurements. So measuring RIXS on a device that is under working conditions. So we can apply electric field, current, thermal gradient, strains, and other things to the sample. So now let me move finally to the third part of my talk, that is the presentation of our results. So from the introduction section, we were left with this question. Can we directly observe magnons contributing to the transport process with energy and momentum sensitivity to understand how actually the energy is flowing and how the transport process is actually realized? So to answer this question, we are proposing resonant inelastic X-ray scattering as our technique. So next, we need to identify a suitable material. We need then to realize a device for magnon transport compatible with the RIXS setup and ultra-high vacuum conditions we need to satisfy. And last, we need to demonstrate that this technique is actually sensitive to non-equilibrium magnon transport. So regarding the material, we selected Yttrium Iron Garnet. That has this Yttrium 3 Iron 5 Oxygen 12 chemical formula, and it is a ferrimagnetic insulator with a Curie temperature of 560 Kelvin. To the left here, I have the unit cell, which is a pretty large unit cell containing 40 iron atoms. So all the iron atoms are in the same oxidation state, and they have a spin 5 half, but they are coordinated into 2 different oxygen cages. So we can have the octahedral side and we can have the tetrahedral side. And the interesting point is that the spin in this different configuration is aligned in opposite ways. And because the occupation ratio of the octahedral and tetrahedral side is not 1:1, but is 2:3, this essentially is the cause of the residual ferrimagnetism in this material. So now Yttrium Iron Garnet is very well-known material in the context of magnonics. And this is because of its unique magnetic properties. It has a very long range of spin wave propagation, ultra-low Gilbert damping, high crystallinity, so crystals can be done in very big dimensions. And for these reasons, it's highly used. And another factor that is pretty relevant that makes this insulator standing out with compared to other material is a very high Spin Seebeck coefficient. And this has been measured in particular, is used in particular at low temperature. As you can see here, the Spin Seebeck coefficient of Yttrium Iron Garnet has a strong temperature dependence, which is peaking around 80 Kelvin, which corresponds also to the maximum of the thermal conductivity. So which means basically that when the phonons have a very long lifetime, now the magnon transport has its best efficiency here. So with this, let's say that then we have selected not only the material that is Yttrium Iron Garnet, but also how to generate magnon current in this material that is by Spin Seebeck effect. So next, we need to realize a Spin Seebeck based device for our RIXS experiment. And this is what the results are, what I'm showing here in the left picture, where it is a bit of overcrowded image to understand the details of our device, but let me then use the sketch in the center here. So first of all, to have a Spin Seebeck device, we need to realize a thermal gradient across our sample. So this rectangular shaped piece of crystal here is our Yttrium Iron Garnet, and it is sandwiched between a cold source, that is what we call our cryostat extension on the side, with a copper piece, and a hot source, which is realized by a microelectronic heater. So in this way, the thermal gradient goes then from left to right, where the cold source set our temperature T, that is the base temperature of the cryostat, and the heater sets our high temperature N, that is T plus delta T. And in order now to know our delta T, we implemented a thermocouple wire across the edges of our crystal to get access to the thermal gradient realized in our device. Furthermore, to make sure that we really have magnon conductivity active in our device, we also deposited a platinum electrode on the side here, and we measure the Spin Seebeck voltage across this electrode. This is the results of our measurement at 300 Kelvin, where we I'm plotting here the Spin Seebeck voltage as a function of the delta T, the temperature difference across the crystal, and you can see now that we have this linear behavior of the Spin Seebeck voltage as we increase the temperature difference across our crystal, which means that the magnon current then is increasing as we increase the temperature gradient. And for our RIXS measurements, we always kept monitoring the Spin Seebeck voltage and the temperature differential across our crystal to make sure everything was functioning and alive during the long RIXS measurements. So next, let's take a look at the RIXS response of Yttrium Iron Garnet in what I call equilibrium condition. So just how a standard RIXS spectrum looks like in this material. As I mentioned before, the first step for doing RIXS is to measure the X-ray absorption of the material and then select a resonant energy to perform our resonant inelastic X-ray scattering measurements. So this is the X-ray absorption of Yttrium Iron Garnet at the iron L edge, which corresponds to the 2p to 3D transition. And for our RIXS measurements, and this we measure with circular polarized, positive and negative polarized polarizations. And we selected the energy indicated by the blue arrow here, which correspond actually to the majority sites, to the iron D tetrahedral sites. And we pick this resonance to maximize actually our magnetic response, being sensitive to the majority iron sites. For our RIXS measurement, then we use a energy resolution that is 20 milliV. And this is actually a representative RIXS spectrum at room temperature and at a fixed Q, where the momentum here, it is actually 0.2, 0.2, 0.2 in reciprocal lattice unit. And as a representation of where this momentum is compared to the surface, it is actually parallel to the surface of the sample, which is indeed as this 111 axis here. So now, what we see in the low energy sector of our RIXS spectrum is a large number of peaks that are overlapping peaks up to 150 milliV. And to actually understand what they are, we use the dispersion known from inelastic neutron scattering for this material. And in this way, we could successfully identify all the modes that actually are part of the Magnon dispersion of Yttrium Iron Garnet. And again, because we are dealing with 40 atoms in the unit cell, that's why we have so many Magnon branches for this material. So starting from the, at 0 energy, we have our elastic peak, and then around 10 milliV, we can find presence of another peak that correspond to the acoustic ferromagnon mode. And in here, I'm selecting the Q that we use for our measurements. Around 50 milliV, we have a strong peak that is likely the collection of all these optical branches here. And at higher energy, we have another peak that corresponds to the higher energy optical magnons, while we still have spectral weight above 100 milliV, where no single magnons should be present, but it is very common in RIXS to find peaks associated to multi-magnon processes. And because we are measuring at room temperature, you may notice the presence of finite spectral weight in the negative energy loss region, which is actually due to the presence of anti-Stokes mode. So next, let's see what happens when we now start to be in non-equilibrium. So we activate our device and we generate a thermal gradient around 15 Kelvin at 300 Kelvin. And now we measure again our RIXS spectrum. So in here, you can find now the purple spectrum, that is our equilibrium measurements, as I just discussed in the previous slide. And in red is the RIXS spectrum measured at the presence of Magnon current. So let me also specify that the Magnon current and the momentum relationship for this spectrum is as illustrated here, such that the momentum transfer is parallel to the Magnon current for this measurement. So if we look at our spectra closely, we may notice that as a function of temperature gradient, we have two regions in the spectrum that are actually changing. So the first change is around the optical Magnon region, around 50 milliV, and we notice a dampening here as we increase the temperature gradient across the sample. But this Magnon dampening can be actually explained by an average increase of temperature. Instead, in the low energy region, we see that as we increase our temperature gradient across the crystal, we have an increase in spectral weight. So now, this is a bit of counterintuitive because cannot be simply explained by average temperature increase, as it should actually cause a decrease in intensity. So it may be a hint of some non-equilibrium response in this range. But to better understand if this is true or not, let's actually change our experimental condition. Let's verify what happens when we cool down and when we actually reach the maximum of the Spin Seebeck conductivity. So let's see now what happens at 80 Kelvin then, where there is this peak in the Spin Seebeck coefficient. So again, I'm now plotting similar type of measurements now at 80 Kelvin, where we start with a dark blue for the smallest temperature gradient across the sample. And we can take a look now what happens as we increase the temperature gradient from 8 to 15 to 24 Kelvin. And we can see now that the main change is actually only around the quasi-elastic line. So by zooming it here, the spectra, now we see that the RIXS differential shape is mostly centered around 10 milliV, and it has a shape of like a single peak, as if only one excitation mode is mostly changing as we increase the temperature differential across our sample. And interestingly, this energy matches the energy of the acoustic magnon in the material. So we can deduce that the acoustic magnon intensity is very sensitive to the temperature gradient at 80 Kelvin. Now let's do this test. Let's now switch the direction of momentum. So before, momentum was parallel to the magnon current. So now let's see what happens when the momentum is anti-parallel to the magnon current. So we repeat the same type of measurement for the same type of temperature gradient. And now what we get is that the RIXS intensity is decreasing as we increase the temperature gradient. So this is again zoomed in the central panel here. And the decrease in intensity again is peaked around 8-10 milliV. But it has opposite behavior with respect to the positive Q. So now, how do we understand these responses that we see in RIXS as a function of the temperature gradient across our device? So can this be due then to the magnon current? So let's make some consideration. So the first consideration from the raw data is to take this RIXS differential line shape. So by taking the difference of the highest with respect to the lowest temperature gradient, and then we integrate the spectral weight, we plot it as a function of the temperature gradient, and we can see that we obtain an almost linear behavior between the intensity and the temperature gradient, both at plus Q, that is represented by the circular markers here, and at minus Q, that is represented by the triangle here. So if we want to look simply at the absolute values, we just flip the triangles here, and we have an overall linear response of the RIXS differential spectral shape versus delta T, which is kind of mimicking the magnon current behavior with respect to delta T. Another point we can consider is the overall temperature-dependent response. So let's compare the RIXS differential response at room temperature in red with respect to 80 Kelvin in green when we consider the same temperature gradient, temperature differential, that is like 15 Kelvin. So we can see that at around 10 milliV energy, the amount of spectral weight differential is 3 times when we are at 80 Kelvin with respect to room temperature. And this scaling factor is actually very similar to the scaling factor of the Spin Seebeck coefficient between room temperature and 80 Kelvin. So another element that points to the sensitivity of RIXS to the magnon current is actually the very peculiar plus and minus Q asymmetry. So as we have seen before, when momentum is transferred parallel to the magnon current direction, the spectral weight in the RIXS spectra increases versus delta T, while it decreases when the momentum is anti-parallel to the Magnon current. And to really understand this behavior, there is only one picture that we can invoke here. That is the non-equilibrium state induced by the presence of the Magnon current. So when we are in equilibrium condition, as represented in this central sketch here, the magnons, the number of magnons per q direction should be symmetric everywhere. But when we induce a phenomenon like the Magnon current, now we are breaking the symmetry, and the numbers of magnon propagating in the direction parallel to the Magnon current, that is going from right to left in this sketch here, is now different from the number of magnon propagating in the opposite direction, that are like represented by the blue magnons here. So because of this Magnon current propagation, we are now breaking the symmetry, and we are essentially introducing a distinction between the plus q direction that is parallel to Magnon current and the minus q direction that is anti-parallel to the Magnon current. So if we put then all these three elements together, we can basically conclude that yes, our RIXS signal, it is sensitive to the Magnon current in our device. And more quantitatively now, we can think about expressing the RIXS cross-section for Magnon excitations as displayed in this equation here, where we basically have a direct proportionality of the RIXS cross-section to the Magnon distribution function for the Stokes channel, where we actually create excitations, and for the anti-Stokes channel, where we actually annihilate the thermally populated magnons. So then the task we have here is now to understand how actually the Magnon distribution function is changing when we are at the presence of a temperature gradient. So to express this equation here, we recur to the non-equilibrium Boltzmann distribution. So few hypotheses have to be introduced, and let's consider then the linearized expression of the Boltzmann non-equilibrium Boltzmann distribution when we are dealing actually with a small deviation from the equilibrium condition. So under such a circumstance, we can express then our Magnon distribution function with this equation here, where I'm now introducing few parameters like tau q, that is the Magnon relaxation time at a specific q. And then we have the null q, which is Magnon group velocity at a given q. And then we have the Magnon frequency omega. And we need to keep in mind that for this expression, q is defined parallel to the Magnon current. So now to solve this equation, the next step that we can use is actually the explicit relation for the group velocity, which depends on the Magnon frequency. And because now we can make an additional assumption where all the transport process is based on the acoustic Magnon, then we know that the acoustic Magnon can be expressed with a simple parabolic dispersion function, which is known for Yttrium Iron Garnet. So we can use this relation here. And the first thing that we can notice is that since the relationship is symmetric in plus minus q, what happens is that when we express the group velocity by the derivative of omega versus q, we find out that this derivative here is changing sign when we are changing from plus q to minus q. So for plus q, the derivative here is positive. So the group velocity is positive, while when we are at minus q, the derivative is negative. So group velocity is negative, meaning that the sign of this old term here is switching as we switch q, which means that the variation in the Magnon distribution function between non-equilibrium and equilibrium, it is sensitive to the q direction, which is strongly recalling our observation here. And indeed, for a visual comparison, let's now compute the non-equilibrium Magnon distribution function using the YIG related parameters here. And for the momentum related to our study, that is this QO2 at 2.2.2 in the reciprocal lattice unit along the 111 direction, we see that as we increase the temperature gradient, the Magnon distribution function is increasing when Q is positive, meaning parallel to the Magnon current, while when we consider negative Q, then the Magnon distribution function is effectively decreasing as we increase the thermal gradient when Q is anti-parallel to the Magnon current. This behavior is exactly what it has been observed in our data. So we can straightforwardly conclude that RIXS probes both equilibrium and non-equilibrium Magnon distribution, and it is sensitive to the Magnon current. And more importantly, because we have this energy and momentum selective probe, we are identifying the mode, the Magnon mode that is contributing to the transport. And we conclude that the acoustic Magnon then has a key role in the Magnon transport phenomena, even at a finite Q. That is what we measured in this experiment here. And for an even more quantitative analysis and insight into this Magnon transport process, gaining microscopic information, we can now analyze the quantitative RIXS spectral weight we observed at fixed Q as a function of temperature gradient. So we can formulate this AQ, that is the integral of the Magnon intensity from our data, as being proportional to a factor that depends on the Magnon RIXS cross-section times the Magnon distribution function. And since we have the relation for the Magnon distribution function, we can now essentially extract by fitting our data of the integrated Magnon spectral weight for positive Q and for negative Q as a function of temperature gradient. We can then solve this equation by extracting these two missing parameters, where the most important one and relevant one is the Magnon relaxation time at a specific Q. What we find is that the Magnon relaxation time at this Q is around 58 nanoseconds. So this value is in line with previous results found at Q equals 0, and assuming then a decrease of Magnon relaxation time for increasing Q. But other than that, there is really no knowledge about how the Magnon relaxation time should evolve with Q. And by having access to these parameters, it actually opens the way to calculate all momentum-dependent parameters like heat conductivity and Spin Seebeck conductivity at a fixed Q. And ideally, by measuring then, performing this measurement as a function of Q, one can then integrate and obtain the macroscopic heat conductivity or spin conductivity for a material without actually using estimated parameters. So in conclusion, I hope I convince you that we performed the first microscopic investigation of Magnon spin current with energy and momentum resolution, and we reveal the Magnon mode that is behind this Magnon transport process. For doing that, we have used RIXS, that is a technique sensitive to different types of collective excitations like magnons, but also phonons, orbital excitations, charge excitation, and their momentum dispersion, and also sensitive to the equilibrium and non-equilibrium distribution functions. The approach that has been presented based on RIXS can extract momentum-dependent microscopic parameters that would not be accessible otherwise, And as an outlook here, this overall approach can be actually extended to different type of exotic form of transport, which are based on collective quasi-particles. Not only magnons, but also phonons, excitons, orbitons, polarons, and in a large variety of materials. So with this, I'm going now to my acknowledgement slide. I really want to thank all my group here at the SIX Beamland of NSLS2, in particular my postdoc at the time, Yanong Wu, who did all the hard work behind this project. We also had tremendous help from colleagues from Center for Functional Nanomaterials here at BNL for the realization of this UHV compatible device. Theory support was provided by Gerrit Bauer and Joseph Barker, and they've been invaluable for the data discussion and understanding actually what we were really seeing from our RIXS experiment. And finally, we got also a lot of support from these various people here, both for the sample characterization and for the design of our device. And then finally, let me thank you for your attention.
Yeah, thank you. Thank you very much, Valentina. Yeah, very interesting talk. Yeah, I actually have a several sort of okay. So let me get the other people to ask first, and then I'll ask. Yeah, Volvok.
Thank you very much. My question is, so if you apply the current perpendicular to the momentum that you're measuring, you expect no change. Is this the correct assumption, and did you check that?
Yes, yes to both.
So you measured in the perpendicular direction, and there is no change whatsoever with respect to
that
temperature.
was actually a much easier geometry for our technique to perform, and actually was the starting one, because to be honest, before initiating this project, we didn't have a clear, let's say, honestly, idea how to measure this Magnon current and where to expect signal. So that was the very first geometry we attempted, with a very disappointing result. That was no change whatsoever.
And can you say if there's like some time resolution to this technique, or is it you can only measure in DC basically? So suppose there's some transient spin current, let's say optically generated or something like that.
So in the mode I've presented here from synchrotron, you don't get much of a transient, unless really something that could happen in the intermediate state, because of the presence of the core hole. There is a lifetime associated with the core hole presence there, which for other type of excitation is actually crucial to determine their intensity. But here we are talking about femtoseconds, like few femtoseconds. Otherwise, I would say free electron laser you need to use.
Thank you.
For a real-time dependence.
Thanks.
Yeah, so I have several questions, Valentina. Yeah, so the first question is in the real Seebeck, spin Seebeck coefficient measurement, you would also apply, need to apply an external magnetic field, right, to sort of align domains. Have you done that in your measurement?
Yeah, for two reasons indeed: to saturate the magnetization of our little crystal, and to measure the spin Seebeck voltage by inverse pinhole effect. So we had, let me go back, excuse me, okay. Okay, there it is, H.
Oh, I see. So I mean, so technically that's actually sort of quite difficult. I mean, have you tried the measurement without the H? How much effect is, how smaller it will be?
No, we didn't try. We didn't try because at the same time, I mean, I think pragmatically, if you do it without, I think you should still see something, or you can maybe magnetize your crystal before, or rely on, I mean, not too many domains. But the reason why we didn't do without it, it's because we need it to measure the spin Seebeck voltage.
Oh, you're basically doing it simultaneously, right?
Exactly. So then,
yeah. But you don't really for spectroscopy, you don't really need platinum, right? I mean, the effect should still be there whether you have it or you have not the platinum, right?
Very true. But because, let's say, for the next one, I would feel comfortable doing it without platinum. But for the first time, I wanted to be sure that there was magnon transport all the time.
I see. So the other question I have is that
Yeah.
in your entire measurement, you've been focused on the energy scale of a 10 millivolt. Why is 10 millivolt important?
You mean why nothing else happens at higher energies?
Yeah. I mean, because the RIXS, can have a very, very, higher energy range, right? You can, in principle, change your resolution and try to measure different energies and see, how different energies were contributing to this spin current, right?
Exactly. So that is indeed was one of the motivations behind it, and we focus on the 10 milliV because that's where we could only observe changes. So we do not really need to do anything during the RIXS measurement to get higher energy excitations. We just get them up to 10 eV. So I have the whole RIXS spectrum. I mean, I didn't have it in these slides here, not in the extra slides, but we have the whole RIXS spectrum up to 10 eV. Then if you are looking for changes, the only change you see are in that low energy sector.
I see, but then wouldn't you expect that if you only see, spin Seebeck coefficient changing, you would expect it to be, greatest, right? As you gradually even, decreasing the energy even more, right? 10 MeV, 9, so it should in principle be most efficient near the quasi-elastic line, right? I mean, except for the gap.
So if you would, if we would repeat this measurement at smaller Q.
Yeah.
So means smaller acoustic magnon energy, then the change should be stronger.
Yes. Did you see that?
Because of geometrical constraints, could not do with this device. I cannot change the Q transfer parallel to the magnon current.
I see.
Because it's a three-dimensional material. So we need to either do then, that's what we are planning to, a different geometry and maybe using not spin Seebeck, but another type of magnon current source. And then we can tune Q. So in this very first demonstration, we focus on this plus Q minus Q.
I see. So you also checked that when there's no temperature gradient, your plus minus Q intensity completely obey the Bose population factor, right? As you would expect, right?
I mean, the plus minus Q pure magnon excitation in equilibrium, they are modulated mostly tiny bit by RIXS cross-section because we need to change the geometrical condition a little bit. And there is a small change.
I see. No, actually, I asked the wrong question. I mean, I guess the energy gain and energy loss at the same Q, does that actually follow the detailed balance factor, right? Okay.
Yes.
Okay. Thank you very much. So
that's
any other
why
questions?
Indeed it is present at room temperature mostly, and when we cool down, excuse me, you have nothing almost there at 80 Kelvin as anti-Stokes.
I see. Okay, thank you. Yeah, Matt?
Thanks. This is very interesting. So this was all dealing with acoustic magnons, right? Looking ahead, do you have any thoughts about, optical magnons and that energy regime?
It would have been nice to find out that optical magnons were having a significant role in this transport process, but actually the reality is pointing to not much going on at that high energy. In particular, because Yttrium Iron Garnet has a very special optical magnon mode with a parabolic dispersion. I mean, one would have questioned if this also, strongly dispersing magnon mode was contributing, but let's say, experimental evidence suggests that not much is going on at higher energy in terms of involvement in the Magnon process.
Thank you.
Yeah. Any other question from the students? Okay, I mean this setup is very exciting. I mean we're hoping to potentially sort of try to redo this with neutron scattering, but it's very difficult. Yes, thank you very much, Valentina.
I mean, you will have the benefit of a much better energy resolution, and if you can overcome experimental challenges, then it would be tremendously interesting to see how indeed.
No, we would, but the problem is that the sample required the volume fraction would require to see signal, yet the temperature gradient, because our sample is typically 2 centimeters.
Yeah.
To generate the temperature gradient you on your sample, it's much more difficult for us.
Yeah, I mean, unfortunately, let's say I have these limitations very clear in my mind. That's why I think that our technique can be a very good complement to inelastic neutron scattering when going in these directions. It's not easy, but it's easier.
We can potentially overcome the difficulty, but I'll let you know when we make some progress.
Yeah.
Again, thank you very much.
Thank you so much. Thank you.
Thank you.
Bye-bye.